probability density functions, or probability as area. How do we visualize continuous random variables? The idea is to introduce something similar to the probability distribution functions that we used for discrete random variables, and we call these probability density functions. And we visualize these using a graph. The idea here is that the probability is the area under our curve. So for instance, if we want to look at the probability that x is greater than minus 0.5, so over here, and less than 1, we look at everything that's above this interval and below the graph of my function. And we look at that area, and that area is the probability. Specifically, the probability that x is greater than a and less than b is the area under the curve y equals f of x between x equals a and x equals b. A couple of properties of these PDFs. If f of x is the PDF of a continuous random variable x, then all points on the graph must be between 0 and 1 inclusive. The area under the entire graph must also equal 1. So that first thing is the same reason as we had with probability distribution functions, namely that probability can't be negative and it can't be bigger than 1. And the area under the entire graph must equal 1 because that entire area represents the probability of the event something happens, which is always 1. Okay, so how do we calculate? In general, you need to use integral calculus. However, if the PDF, which is short for, in this case, probability density function, is nice enough, you can use geometry. Let's do an example. Consider the continuous random variable x with PDF this. Its graph looks like this. Well, to start with, is this indeed a valid probability density function? Well, all the values are between 0 and 1 inclusive, as you can see from looking at this graph. And when I look at the entire area under the graph, I need to know, is that 1? Well, I want to look at this area here. To compute this, well, this is the area of a triangle, so I can use what I know from geometry, that the area of a triangle is 1/2 times the base times the height. Well, the base of this triangle is 4, and the height of this triangle is 0.5. 4 times 0.5 times 1/2 is 1. So indeed, the area under the entire graph is 1, and so this is indeed a valid probability density function. Okay, so what's the probability that x is less than 3? In other words, what is this shaded area? So notice here, I've shaded everything that is under the graph that is over the interval x less than 3. Since everything to the left of the y-axis, since the function is 0 there, I don't need to shade anything there because there's no area there. There's no area here. I only need to care about this part. Well, to figure out what this probability is, I do the same thing as before. I do 1/2 times the base times the height. 1/2 times 3 times, well, what's here? Well, this height here, that's exactly the value of our function at x equals 3. So this is f of 3 equals 3/8, and so the area is 1/2 times 3 times 3/8, which is 9/16. And so the probability that x is less than 3, which again is our shaded area, is 9/16. Okay, what's the probability that x is greater than 1 and less than 3? In other words, what is this shaded area? Well, since I don't have an immediate formula at hand for the area of this weirdly shaped quadrilateral, what you want to do is turn this into something about triangles in this case. Well, I can look at this in many ways, but the way that I'm going to do it is it's this area, the area enclosed by this triangle, minus this smaller area here. So let's compute these areas. Well, the big area we've already computed, that's 9/16. For the small area, well, the base is 1, and the height is f of 1 is 1/8, and so that area is 1/2 times 1 times 1/8, which is 1/16. And so the probability that x is greater than 1 and less than 3 is 9/16 minus 1/16, which is 8/16, or 1/2.